to cover. Before we get started, everybody, in case you've managed to miss it so far, your midterm is on Monday. And given how few people were in my office hours this morning, I expect you to all get perfect scores. Yeah? By the way, speaking of how few people were in my office hours this morning, I am willing to add some additional hours this week because you do have a midterm. Show of hands, would Friday afternoon work? Friday after section? Sunday afternoon? Okay, so it's like the same people for all three, so I'll just choose one and post on Piazza sometime the next day or two. If I don't, then send the usual nasty email and I will do so promptly. Right, your midterm is going to be some number of questions that I have yet to determine. Is that useful information or what? You're allowed to bring one 8.5 by 11 sheet of paper. I don't care if you type it, I don't care if you write it, I don't care if you use some chemical process, but no magnifying glasses. You laugh, but I've actually gotten that question multiple times before. Yeah. So anyway, yeah, this is going to be, you guys have probably figured out by now that my main focus is on problem solving rather than regurgitating algorithms and just computing QR of things. So you probably can guess what type of midterm this will be. Hopefully it won't be so hard. I'm trying, and I'm going to ask your TAs to take the midterm and make sure that at least they can take it before you guys do. Yes?
So that's two sides of a sheet.
Two sides of one sheet.
Could we make two sheets with one side?
No.
No.
Yeah, no, just one sheet. Just keep it easy. Yeah. Sorry. Any other questions? Going once, going twice? Okay, yes?
Would it be beneficial, for bringing the sheet to, write down a Gram-Schmidt, process on that, or is that, the kind of thing,
what you put on your sheet is your decision.
I was wondering, how specifically should you know,
You are responsible for all the material in this class through today's lecture. Can I provide any more specifics about the midterm? No? Alright guys. Yeah, I hate to be vague. I promise it won't be so bad. I mostly want to make sure that you guys, again, remember the big takeaways that I want you to get from this class, is that I want you to know when to use which algorithm where, and have some idea of when they work, how they work, and when they fail. Yeah? I'm not looking for super detailed, you can implement pivoted whatever the heck at home and have the perfect numerical stability and compatibility with IEEE, floating point, whatever the heck is not important to me, because thankfully there are people that exist in this world that have taken care of this in a very stable way. What's much more important, what I think is really valuable, especially for sort of a lower level course like this, is that you guys can appreciate when these things are useful and when you might apply them. Yeah. So yeah, and so it's mostly numerical linear algebra and some of the optimization and root finding we've done this week. Cool. And meanwhile, has anybody tried the extra credit? No? You ask for coding assignments and then you don't do them. So there's no winning here. Cool. Well, if you do them, then you can get late days, and that's cool. Okay, great. Anyway, we have a lot to cover today. Chances are we're not going to keep up with the schedule. I keep saying that, and then we actually do. But I think, actually, I was looking at my lecture for today, and it's ridiculously long. So chances are we'll continue, I guess, next Wednesday after your midterm, and such is life. Obviously, you're not responsible for material that I don't hit today. Cool? Right. So last time, we were talking all about the root finding, the different types of algorithms for finding roots of equations. Right? Remember, roots here are not square roots. They are zeros of functions. Yeah. So what we're trying to solve is finding x where f of x equals 0, where basically I want to write a generic piece of software that I give my software an f, and it gives me back that x where it's a root. Yeah? And last time we covered a couple different algorithms for finding roots in the single variable case. That is, f has one input and one output. Right? And I promised you guys that we would come back and try and consider algorithms where we do root finding in multiple variables. So now f takes in several numbers and it gives out several numbers. Yeah? And this is a considerably harder problem. Okay, so again, today's root problems are not f from R to R, but rather f from Rn to Rm. Cool? Hopefully we're all comfortable with this notation. By the way, something I do expect as sort of a side, thing that you should know from this class for your midterm, for example, would be notation like what you see on the board and some of the set notation we've had, as well as some linear algebra. Sorry. Okay, so, right. Have we talked about root finding? The answer is yes, in one very easy case. Right, you guys will notice throughout this course, I'm going to keep returning to the same example, which is solving linear systems of equations. And in fact, unsurprisingly, just like you can solve it variationally, you can also solve it using root finding. Because if I define f of x to be ax minus b, where are the roots? Well, it's when this thing equals 0, or in other words, when ax equals b. Yeah? But of course, for other f of x, for example, if they contain cosine, sine, arctangent, exponents, Fourier, whatever the heck, then we don't get so lucky and Gaussian elimination no longer applies. Right? So before we proceed, it is worthwhile to kind of think about this problem at a high level. First of all, so again, f is going to take n input numbers and give m output numbers, and generally we assume that the number of inputs is at least as large as the number of outputs. Why do we do that? Well, let's think for a minute what would happen otherwise. So let's say that I have f of t, right? So he's just taking in a number in R1. That's a 1. Right? But maybe f is really a vector, and it looks like f1 of t, f2 of t, all the way to, f100 of t. Now, what would it mean to find a root of this potentially nonlinear equation? Well, it's sort of like asking that 100 different things be 0 all at the same time, and you only have one parameter, right? And the likelihood of this happening at all is very small. It's sort of like trying to solve an overdetermined system of equations, right? So in general, we assume that the number of inputs is at least as big as the number of outputs. So for example, functions like f of x comma y equals xy. In fact, this thing, right, he has 2 inputs and 1 output, has a lot of roots, you know? So, right, for example, anytime x or y is 0, it's got a root, so lots of roots. So anyway, this is useful to keep in mind, right, that generally the algorithms that we'll talk about for multivariable root finding are going to be successful in this case, and they will fail in really creepy ways in this case. But that's sort of okay, because you kind of expect it to fail. The problem is a little bit poorly conditioned, poorly defined in that case. Cool? All right. So, if we jump right back to the kind of stuff we were doing in the last class, remember the most successful method we had for root finding was this thing called Newton's method, at least if we have a pretty good initial guess. Right? Newton's method had all this nice quadratic convergence properties and so on, and basically it was just some iterative scheme that took a function in its first derivative, walked down the first derivative to what it thought was the root, and then just kept correcting and slowly kind of moving down the slope. Yeah? Does this story sound familiar? It should. Cool. So our first question today is going to be, how do we extend Newton's method to more than one variable? And the sort of underlying question there is, well, for one thing, how do you take the derivative of a function of more than one variable? And hopefully you remember this from Math 51 and or equivalent. But basically we're going to define this object called the Jacobian. Right? We call him df, and he's a matrix. This is for f going from Rn to Rn. And basically, what's going on here, and by the way, I have a huge propensity, probably at this point you're not surprised, of swapping these i's and j's by accident, so if you see a typo, you should tell me. But anyway, right, so entry ij of this Jacobian matrix is equal to the partial derivative of the ith component of f, right, the ith output, with respect to the jth input. Right? So this is all the possible ways we can differentiate all the possible pieces of f. That's all the Jacobian is. Nothing too complicated. Alright, so, sanity check, and because I always get the answer to this question wrong, somebody tell me, how big is df? What size matrix is this guy for f going from Rn to Rn? N by n, right? Because the i's, let's see if I did this right. So the i's index over all the outputs, right? Oh, sorry, m by n. No, in fact, I did it wrong. Right, because the i's index over all the f's, right? Those are all the outputs. And the j's index all over all the inputs, so those are n. So there are n j's and m i's, so it's n by n. Yeah? See, I already got it wrong. I'm going to do this like 7 times today, so you guys should catch me, okay? Cool. All right. So just like we can write a Taylor series for a function of one variable, we can do a similar thing for functions of multiple variables using the Jacobian. And thankfully for us for now, expanding, in about 10 minutes this isn't going to be true, but for now, expanding just one term, right, a linear term, in our expansion is good enough, right? So to first order, f of x looks like, well, f at some x sub k, you can probably see where I'm going with this, plus the Jacobian matrix now times the difference of x minus x sub k. Okay? This is kind of reasonable, right? This looks just like our usual Taylor series approximation, right? Which says that f of x equals f of x, right? In a single variable, it would look like f prime of xk, right? So this formula and that one are quite similar. All right. So thankfully, deriving Newton's method was pretty easy from here. Remember what Newton's method did? We wrote down the first order approximation, and then we just solved this thing for x, and that gave us our xk plus 1. Well, we can do exactly the same thing here if we apply df inverse, yeah, and then do a little bit of shuffling. And in fact, Newton's method works as advertised in multiple variables, and it's very easy to implement. Right? It's exactly the same as it was before. Right? You take your previous iterate, you evaluate it using f. You basically divide by the derivative. Right? Now division has been replaced by matrix inverse, and you use that to increment your previous estimate. Okay? So this is just the multivariable version of Newton's method that we already talked about. Right? This is just using linear approximations of f. And just like the single variable version of f, you could do higher order approximations and solve, although usually we don't bother. Cool. So this method. Oh yeah. Quick review question since your midterm is coming up. Do we ever explicitly compute df inverse? Everybody. 1, 2, 3. No, right? Whenever I have df inverse in a formula, in fact, the first exception you will see to this comes later in this lecture. But in general, when you have df inverse in a formula, that means apply df inverse. It doesn't mean compute it and then multiply, right? So basically what's happening there is Gaussian elimination. Cool? All right. Just like we can prove that Newton's method converges in a single variable, which we did in detail in our last lecture. I think I managed for once to do it without making any critical mistakes. We can prove basically using the same argument that this thing converges. I'll leave this for you to check at home. But basically, remember our convergence for fixed point iteration depended on the derivative of your fixed point being less than 1. It turns out the correct way to extend that to multiple variables is to assume that the maximum eigenvalue of your Jacobian is less than 1. Fun fact of the day. And then from there, it's pretty clear that things should converge by pretty much exactly the same argument. In fact, and they converge quadratically. Yeah, so try and construct this at home. It's a good exercise. And you can Google. It's a very common proof. All right. But for now, since we got a lot of material to cover, I'm going to have cloud forward. So we have two problems. One I mentioned last time, which is that differentiation is hard. Right? So if I have a really complicated function whose roots I'm trying to find, right? Like one that requires me in the back, behind the scenes. For example, maybe I'm trying to maximize my profit in the stock market, right? And so every time I want to evaluate f, secretly I have to simulate the stock market for 20 years, right? That's a very expensive evaluation of a function, right? And now we're getting these functions with multiple variables. So to evaluate the function and its derivative, we're going to have to evaluate a ton of things, right? And the second problem is that df changes in every iteration. Remember, this is sort of similar to some of our eigenvalue iteration problems, right? Every time we move our estimate of where the root is, xk, we have a new Jacobian, right? And that means that we have some new matrix to factor into inverse or whatever. And because of that, strategies like LU factorization are kind of limited use, right? In particular, every time we change df, the LU factorization is invalid again. Right? So we can't reuse it to keep hammering away at the inverse. So we'd like an efficient root solver, and so far we don't have one. We have a very sort of well-behaved, well-conditioned one, but we'd like to make it faster. All right. So if you kind of parallel our lecture from last time, maybe a reasonable thing to do would be say, okay, remember last time we had Newton's method, we didn't like computing derivatives, so we replaced derivatives with secants, and everything more or less was the same, although it cost us because we went from quadratic convergence to golden ratio convergence. One of my favorite facts. But the problem is that the secant method isn't really obvious how to extend to multiple dimensions. Do you guys see why? Now think about what happened, right? So let's say that I have a function of two variables, right? So really, I'm moving around in the plane. This is R2, right? So we have x and y here, right? And basically, what's going on during these iterations is each time I run another step of Newton's method, I get another approximation of where I think the root is. So I'm kind of scooting around in this plane, evaluating how well how successful it was, and then regrouping and trying again. Right? That's all Newton's method is doing. And then secant says, okay, I'm going to take my last two approximations and just draw a line from one to the next and use that as a proxy for the slope. Yeah? But now, if I'm in like R100, is 2 points enough to determine the whole Jacobian? Even approximately? No, we need 100 points. Yeah? And so keeping track of the last 100 iterations, and in fact doing 100 things just to get started, is not a very practical solution to this problem. Right? So unfortunately, the secant method does not extend in a nice way to the multivariable root finding case. Or does it? So, here's how we're going to get around this. One observation we can make is that although we can't get the full Jacobian from two data points when we evaluate f, we can get the directional derivative. Or we can get an approximation, I should say. Right? So in particular, let's say that I remember I'm stepping around in the parameter plane, I'm guessing all of these different values potentially for the root. Yeah? I look at the last two, each of these two guys has two f of x values. Sorry, it's hard, and you need at least 3 dimensions to be able to do this. But basically, you end up with two different points in space. You can compute the slope between them, and that doesn't tell you the whole Jacobian, but it does tell you the slope between the 2 points that you just checked. Right? We call this the directional derivative of f. Namely, we take a direction in the parameter plane. Right? So let's say that f. Sorry, I should draw a picture. Let's say f goes from R2 to R. Right? What does that mean? Well, that means that there's some parameter plane here. Here's R2, right? And here's R is just the real line, and F is mapping from one to the other, right? So for each point over here, there's some point over there. Yeah? So the directional derivative says, okay, I choose 2 points here, corresponds to 2 points there, and I can compute the slope, of this function just in this little slice of the parameter plane. And now we're back down to one variable again, and life is good. Right? And it turns out that the directional derivative of f in the direction v, I checked by the way, this is covered in Math 51, so technically it's not my fault, is the same as the Jacobian of f times v. This is kind of reasonable, right? The Jacobian encodes all of these different derivatives in all the possible directions, and so in fact you can think of it as an operator that takes a direction in the tangent plane or the parameter plane and gives you back the directional derivative of f. Cool? Alright. So, here's the thing. Let's say that we have an approximation J of the Jacobian. One thing I could ask is that, and this sort of looks like the secant method, right? I could say that my approximation of the Jacobian times my current iterate minus my previous iterate, right? So this is the difference in my 2 points in the parameter plane that I just checked, right? I could ask that this is at least approximately equal to the difference in f values that I just saw. Notice that this does not determine J, but it would be useful if J satisfied this, right? This is sort of a secant-like condition in multiple variables. Hopefully you guys kind of follow the trick that I just did here. I haven't even done a trick, actually. This is just like a potential thing that might be useful. Yeah? And indeed, an algorithm that forces this exactly is called Broyden's method, and you can think of it as sort of the extension of the secant method to multivariable root finding. Cool? So it's not 100% clear how to do this yet, right? That's, right? You think about it. This is a condition on J that says J times some vector equals some other vector, right? But that doesn't determine J at all. That only determines J in one sort of, one dimension of J, right? So what do we do with the rest of J? It's unclear. So what Broyden does is he introduces this idea that really you want J to change as slowly as possible while still satisfying this approximation. This is an interesting trick, and one that we're going to use a few times when we talk about these big nonlinear problems for optimization and root finding. And in particular, we're going to say, okay, our outline is going to be like this. At each iteration of Broyden's method now, we're not going to just maintain our current iterate, right, our current estimate of where the root is, but we're also going to maintain an approximation of the Jacobian nearby. Okay, we're going to update both of these things in each iteration. How are we going to update xk? Well, just using the Newton iteration we had before, right? That's obvious enough. And how are we going to update j sub k? Well, that's less clear. but we're going to try and incorporate this secant approximation I just gave you guys. Cool? Alright. So, I think at this point in this class, hopefully you've seen this theme before, right? Anytime we don't know what we're doing, we write down an optimization measuring things that might be useful, we see what happens at its minimum, and we pray, right? And in fact, that's exactly what we're going to do with Bourdin's method as well in our sort of grand unified theory of all of numerical analysis. So let's go over this in a little bit of detail. So let's say I want to find j sub k, right? Our current estimation of the Jacobian of f near xk, right? Well, we're going to make the assumption that xk and xk minus 1 are kind of nearby, right? So in other words, the Jacobian at these two places is pretty similar. But now we have this additional piece of information, right? Because we have this new secant that we'd like to add to our matrix. So what Bourdin does is sort of the stupidest possible thing. Right? What Bourdin does is he says, okay, well we have jk minus 1, he's our previous Jacobian, and let's just say, well, we'd like the Jacobian to change as little as possible, so I'm going to subtract jk and jk minus 1, I'm going to compute this difference and ask that that number is small, right? And I take the Frobenius norm because that's the easiest norm to work with, right? I think we've seen this now. But I'm going to add the condition that j sub k must satisfy our secant approximation. See what I did? So I'm sort of updating the secant direction in j and leaving the rest of it the same because I don't know anything else. Yeah? Now, of course, if this minimization problem is difficult, then I'm a little bit hosed, right? Because I just replaced a root finding problem with like a hairy minimization and like, great, so I went from something hard to something harder. But in fact, that's not the case. We can solve this in closed form. And let's do that. This is good practice for your midterm, right? Because we're getting kind of good at writing down Lagrange multipliers and minimizing and playing this game, yeah? And in fact, we can do something really cool with Bourdin's method. Like one of my favorite algorithm tricks. As with everything else in 205. Okay. So first let's make a few changes to variables. I'm going to define delta j to be equal to jk minus jk minus 1, and he's going to be our new variable, yeah? And I'm going to define, let's see here, delta x to be xk minus xk minus 1, and I'm going to define d to be equal to f of xk minus f of xk minus 1 minus jk delta s. Okay, now why did I make these weird, Mindy's looking very concerned right now. Why the heck did Justin just make this bizarre set of substitutions? So first of all, if we can compute delta j, obviously we can compute j sub k, yeah? So this substitution is okay. It's kind of clear why we might want this delta x, right? Because we have this, this difference sitting here. But then what happens to our linear condition? Well, so we have jk times this difference equals the difference of f's, but now we have to substitute this guy, right? So when we do that, we're going to say, okay, well jk is really equal to delta j plus jk minus 1, right? And then this guy times delta x is equal to f of xk minus f minus 1. Yep. Now what is known and what is unknown here? This is known, this is known, this is known, this is known, this is unknown. Yeah? So let's move all of the known stuff to the right-hand side. And in particular, you get that this implies that delta j times delta x is equal to d. Right, for this. Cool? So what is our new optimization? Did I write it here? I didn't. Okay. Right. Where did my eraser go? Okay. So now, what do we want to solve? Well, we're still minimizing, but now we're minimizing over delta j's, right? He's our new variable, and it's just the norm. Oh, thanks. Delta j Frobenius squared, right? So this is the same as our energy from before, such that delta j times delta x equals much cleaner. Yeah? That's why I like this form better. So let's solve this thing. How do you think we're going to do it? No? Come on, guys. I got a midterm in a few days. Lagrange multipliers. Yeah? This is exciting yet? Right? We have an optimization with a condition, so we're going to solve using Lagrange multipliers because we have no other hammers in this class to use to solve these kinds of problems yet. And so, what is the Lagrange multiplier function of this thing? Well, it's certainly not that. It is. Alright. Well, let's write out the Frobenius norm of delta j. Remember, that's the sum over I and j of delta j squared. Right? This is just the ijth entry of delta j. Yeah. And now, for my next trick, we're going to say that this is, now we need the Lagrange multiplier of this. And so this is a linear condition. And in particular, one way you could write it would be lambda transpose times delta j delta x minus d. Yeah? Did I do that right? I think I did. Yeah. And right, does this make sense? Right? This is the thing that we want to hold. This is our equality condition. And since there's a vector of them, we need a vector of Lagrange multipliers. Cool? Alright. So in fact, let's expand this guy out. Right? Well, so we're going to say that the lambda times d is just some constant for now, so we're not going to worry about it. He's actually a constant of lambda. But what is this? The lambda transpose delta j delta x. Well, that's the same as the sum over ij of lambda I delta j ij delta x j. And I'll let you guys check this at home. You might have done something like this by accident on your own. Yeah, but that's what this product of this times this times this will give you. Cool. Well, thankfully, this derivative is very easy to take with respect to elements of delta j. Right? We're getting good at this now. So let's do that. Right? So we know that, again, we're trying to optimize this energy. So in the end, we have to take the derivative of the Lagrange multiplier and set it equal to 0. Yeah, I'm getting good at this pattern. And now this is respect to delta j, ij, right? The ij, the element of delta j, you have a whole matrix of unknowns. You see, this is sort of like that metric learning problem nobody likes, right? And then we got a matrix of unknowns here we got to solve for. In this case, it's actually a little bit easier than that homework problem. Sorry. So of this entire sum, right, only one of them is concerned with a particular ij element. So that's 2 times delta j ij, right? Minus, oh sorry, did I do a minus or a plus? I'm going to make this a plus because that's what I had on my course notes. Doesn't matter, right? You can change the sign and lambda. Cool. And in particular, this delta j only survived for one term as well, and that is lambda I delta x j. Cool? All right. So in other words, this tells us what? This tells us that delta j at position ij is equal to 1/2 lambda I, oops, did I do this right? Yeah, minus 1/2 lambda I delta x j. Yeah? Or in other words, that if we vectorize this whole darn thing, delta j is equal to 1/2 lambda delta x transpose. Right? This thing looks like an outer product, remember that word? Cool. This is a good formula, huh? We're getting somewhere. Alright. How far have we got? Well, one thing I could do, now here's going to be our only little clever piece of trickery for this particular proof. I keep losing my eraser today. Which is I'm going to take this relationship here, I'm going to multiply both sides by delta x. Cool? So what is this, what does this do here? Well, if I multiply both sides by delta x, then I get delta j times delta x is equal to 1/2 lambda times the norm of delta x squared. Yeah? Cool. So, now what? Well, what is delta j times delta x? Well, let's go back. We have a name for this from our constraints. Right? So if we substitute this guy in, right, so we'll say he's equal to d. Well, now this is just a scalar, so I can divide by him now. And in particular, what I get is that lambda is equal to what? It's equal to, let's see here, 2 times d divided by mod delta x squared. Hopefully I did that right. Yes, okay. Sorry, this stuff's a little hairy, so I'm going to keep checking myself on my notes. All right. Well, this is good. I just gave you an expression for the Lagrange multipliers in closed form, so I never have to look at them again. Yeah? That's handy. Doesn't always happen. We get lucky with this system. Yeah? And so now we can go back to our formula for delta j and just plug in lambda. Right? And what is this going to buy us? Well, in the end, it's going to say, okay, well, delta j is equal to 1/2, and then what do we have? 2d over mod, I keep forgetting delta x squared, right? That's this formula, times delta x transpose, right? Obviously the 1/2 and 2 cancel, and this is our formula for the Broyden updating. Yeah? This is the delta j in closed form. Everything here is known on the right-hand side. This is tricky, huh? So I wrote down an optimization problem, but in fact, and so what I did here is I substituted back in d and delta x, yeah? But it's the same formula, hopefully. Yes, okay. and this is a way to go from jk minus 1 to jk, and it's just a formula. And secretly we know that that formula is solving this minimization problem upstairs, because we just did it in closed form. And that's the trick to Broyden's method. Cool? So what Broyden does is he says, okay, I want the Jacobian not to change very much, but I do want it to satisfy this new secant that I have, and otherwise we're going to just minimize the difference. And in fact, it turns out that when I do that, I get a nice closed form for how to update j. Yes? Uh-oh, I did something wrong.
Should the matrix jk in the vector d be replaced with jk minus 1?
Yes, sorry. Yeah, this should be j k minus 1, right? And same. And I think in my notes it's probably a typo, so give me a hard time on Piazza and I'll fix it. Sorry. You'll notice that when there's a typo in my notes, it probably needs some slides because I copy and paste it. Cool. All right. So that was our Broyden step. Didn't turn out to be so hard, right? Like algorithmically, this is just a matrix multiply, even if it's like kind of funky how we got to that formula. Yeah? And how do we do the Newton step? Well, we just do Newton's algorithm like we had before, right? We just multiply by j inverse, and we assume this thing kind of looks like the Jacobian of f. And it turns out that this strategy converges, but just like the secant method, it's a little bit difficult to prove it converges in all cases. So we're gonna not write down that proof, but sort of apply our intuition from secant and from Newton's method to argue that it's reasonable that this thing should work at least in some neighborhood of x star. Cool? So, lots of implementation details. So I told you how to get from jk minus 1 to jk, but I didn't tell you what j0 is. Yeah? And this is actually a legitimate issue.